This is Coding Math, episode 19, Bezier Curves. I'm going to take a break from all the physics stuff we've been doing and explore some other topics for a few weeks. So today we're going to take a deep dive into Bezier curves. Now the most important thing to know about Bezier curves is how to pronounce Bezier. When I'm alone in my head, it's usually Bezier because I was taught that ER is But if you're out with your educated friends and you say Bezier, they'll laugh at you. Anyway, Bezier curves are all about linear interpolation, which we covered some weeks ago. Basically, you take a value from 0 to 1 and a range of numbers, and you find a value in that range that corresponds to the initial number. So say you have 2 points. One is at a position on the x-axis of 100 and another at 200. And we have a value between 0 and 1. We'll name that t. Now if t is 0, the output value we'll get is 100. If it's 0.5, we'll get 150, and if t is 1, we'll get 200 as an output. If you have any questions about what all that means, check out Coding Math Mini number 2. Next, let's throw the y-axis in there as well. We'll use the same t to interpolate between x and y at the same time. Now as we build this up, it's going to get a bit complex, so rather than trying to demonstrate what's going on with my crappy drawings, I've gone and made a demo using modern computer graphics. So we have 2 points, P0 and P1. P0 is at position 100, 500, and P1 is at 600, 200. As we go through this, we'll get interpolated values for x and y, which we'll use to make a new point, PA. When t is 0, PA will be the same as P0. When t is increased to 0.1, PA will move 1/10 of the way from P0 to P1, which will put it at 150, 470. As we move t through 0.2, 3, 4, and into 0.5, PA moves to the halfway point between P0 and P1, which is 350, 350. And as we continue to decrease t up until 1.0, PA moves until it sits exactly at P1. And you can see that as it has moved, it's drawn a line. It's not surprising that a linear function draws a line, I guess. Now let's add a third point, P2. It'll be at 1,400. Now we'll continue doing exactly what we're doing, moving PA between P0 and P1 based on the value of t, but we're also going to add a new interpolated point, PB. This is going to move between P1 and P2. It's also going to use t to interpolate, so it'll be right in sync with PA. Now when t is 0, PA is at P0, and PB is at P1. When t goes to 0.1, PA moves 1/10 of the way towards P1, and PB moves 1/10 of the way towards P2. I guess I don't need to beat this to death, you know the rest. So this is drawn 2 lines. But now, instead of rendering the lines that each interpolated point is making as it moves, let's draw the line that goes between them. We do that for 0, 0.1, 0.2, 0.3, and so on up to 1. Well, that's interesting. We're starting to get something curve-like. It's kind of like that string art you did as a kid. Your mom said she loved it, but one day it wasn't hanging on the wall anymore. Now this is where things get meta. We're interpolating between P0 and P1 and P2 to get PA and PB. Now we're going to interpolate between PA and PB to get P final. In this final demo, I'll show P final in red. We'll start with t at 0. So PA is at P0 and PB is at P1. We use the same t to interpolate between PA and PB, which puts P final at PA. At t equals 0.1, PA moves 1/10 towards P1, PB moves 1/10 towards P2, and P final moves 1/10 of the distance between PA and PB. As t continues to increase, we'll track the position of P final. And what do you know? We have a curve. It's pretty low res at this point because we're only drawing it with 10 steps. But if you move t between 0 and 1 with smaller increments, that will smooth right out. The important thing to take note of here is that the curve starts at P0, ends at P2, and moves toward but does not reach P1. If we move P1 and run through this again, the curve changes to move towards P1. So we call P1 the control point. It controls the shape of the curve. Now this is what we actually call a quadratic Bezier curve. And we'll see why we call it that in a moment. Let's go into our utils.js file and create a quadratic Bezier function. This will take 3 points, p0, p1, and p2, and a value for t. It's going to return a point, so we'll create a pFinal as a generic object that we can add x and y properties to. Next, we have to calculate the x and y for pFinal. We could use utils lerp to interpolate between p0x and p1x to get a pax, and then use lerp again to interpolate between p1 and p2x for pbx, and then use lerp again to interpolate between pax and pbx to get pFinal x, and then do the same thing all over again for y. And that would actually work just fine. In fact, that's basically what I just did to create the demos you see here. But that's more lerping than anyone should ever be doing in a single function. If we replaced all those lerp calls with the actual formula that the lerp function uses, we'd wind up with a big, long expression. And if we reduced that expression as much as we could, what we would wind up with is pFinal x equals mathpow 1 minus t, 2 times pox plus 1 minus t times 2 times t times p1x plus t times p2x. And the same thing for y. Now feel free to work this out on your own, but it's the standard function for Bezier curves. So because the highest power in this formula is 2, we have a couple terms being squared, it's a second order function, or a quadratic, thus quadratic Bezier curve. So you pass in 3 points and a t, and it returns a new point. The only thing that bothers me about this is that every time you call it, it's creating a brand new point. And you'll probably be calling this function many, many times for a single curve, so this could be a problem. So I'm going to add an optional final parameter, pFinal, and say pFinal equals pFinal or a new object. This allows the user to create a pFinal on his own and pass it in each time. At that point, we'll just have its x and y properties set with the calculated values. Another option would be to have the function just take single values instead of points and return a single value. So you'd call it once to get the final x value and again to get the final y. I had to choose one of these methods, so I chose to use points in the function. If you prefer it the other way, go for it. I won't argue. Now the other common Bezier curve is the cubic Bezier curve. As you'll soon see, this has powers of 3 or cubes in its formula. Like the quadratic Bezier, the cubic has 2 endpoints, but it has 2 control points as well. This allows for more complex curves and a lot more control over how the curve moves. This just adds on one more initial point, p3. Then you interpolate from p2 to p3 to get another intermediate point, pc, and then from pa to pb for something like pn, and pb to pc for pm, then pn to pm for pFinal. So interpolation 3 levels deep. It looks pretty cool in motion, so I'll animate this and just let it run for a little bit. Now there's a lot going on here all at once. To get a feel for what's happening, first watch the 3 green dots as they move back and forth along the gray lines. Then follow the 2 blue dots as they move along the green lines. And finally watch the red dot as it moves back and forth along the blue line. Then you can see the path that the red dot forms, which is the Bezier curve. So now let's create a cubic Bezier function. This takes 4 points, p0 through p3, a t, and an optional pFinal. And again, we could go all lerp crazy here, but this too distills down to a standard formula, which you can see here. Again, you can derive this by yourself or just trust that I copied it over correctly. Okay, so now we have these nifty functions, but what can we do with them? Well, we could draw some Bezier curves, but most graphics systems already have functions to draw quadratic and cubic curves. Canvas has context quadratic curve 2 and context cubic curve 2. There's no doubt that these are more optimized than what we just created, and much easier to use, so that doesn't make sense. But ours can do things that theirs can't. In the file main1.js, I've set up 4 points plus a final point, and randomly place them on the canvas. I then draw circles for each point, and then use Quadratic Curve Tool to draw a curve between them. Then I loop t from 0 to 1 in increments of 0.01. In that loop, I'm calling utils quadratic Bezier with all the obvious parameters. Then I'm drawing a small circle at p final x and y. Here's the result of that. So, you can use this function to draw Bezier curves with shapes instead of just a line. Or to look at it another way, you could use it to distribute shapes along a Bezier curve. You can also animate the drawing of a curve using these functions, something you can't do with the built-in curve functions. The file main2.js has a similar setup with 4 random points, but then uses a request animation frame loop to create an animation. This increments a variable called maxt and uses utils cubic Bezier to draw a curve from 0 to whatever maxt is. When maxt exceeds 1, it gets set back to 0. Here you can see the curve as it is being drawn rather than just having it appear all at once. In one final example, main3.js has an object moving along a Bezier path. Same basic setup. The curve is drawn using the built-in cubic curve tool function, then a point on the curve is calculated using the current value of t. A circle is drawn at that point and t is incremented. When t goes past 1 or 0, the increment value reverses. And so what we get is an object moving back and forth along the curve. So there you go, Bezier curves. I've only given you a few quick examples of how you can use them. I hope you find it useful. Also, all the code for the initial demos will be included in the usual GitHub repo for this episode. It's not very pretty as I just hacked it together for the demo, but you might find that interesting as well. See you next week.